Hello everyone. In this lesson we continue our discussion on the derivative. In particular, we're talking about the derivative of a function. So in this lesson we graph the derivative of a given function and state the connection between derivatives and the original function, derivatives and continuity. Describe the conditions for when a function does not have a derivative, and then we'll finish by talking about higher order derivatives. Now, the derivative of the derivative function gives the derivative of a function at each point of the domain of the original function for which the derivative is defined. So recall our formula based on the definition of the derivative from the last section, where we had f prime of x as our derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Right? Now, if we have a function f of x is equal to radical x, then if we do f prime of x, that is going to be equal to the limit as h approaches 0 of the f of x plus h. So where we see radical x for this part, we replace it with radical x plus h, then minus f of x, which was radical x all of h. And if we continue by multiplying by the conjugate and so on and so forth, and simplifying that all the way down, and then plugging in h equals 0 at an appropriate time, we'll end up with 1 over 2 radical x. So if you did all the work between here to the end, you should get your derivative function being 1 over 2 radical x. Now, if we graph these two functions together in the same plane and compare them, here we have f of x is equal to radical x in the blue, and f prime of x being equal to 1 over 2 radical x. Now notice what is happening between these two functions. Notice that original f of x is increasing over the entire domain. So the slopes are positive slopes of the tangent lines. If we drew tangent lines, it would all be positive at each point, but it is getting smaller and smaller and smaller positive. Right? The derivative function, therefore, is always above our horizontal axis. They're all positive values. However, even though they are positive values, because our rate of change is decreasing, the positive, then that is why we see the numbers going down. They're decreasing in our derivative function. All right, so that is what is happening. So in general, if the derivative f prime of x is less than 0, that means it's negative if our original function was decreasing. And the derivative is always greater than 0, always positive, where our original function is increasing. And finally, the derivative is 0, where the original function has a horizontal tangent. Now we can use these ideas to sketch the derivative of a function. Notice here, with this function, we're just given f of x, the zeros exist where the tangent, right, is 0. We can have a horizontal tangent, the derivative is 0. So we're going to plot a derivative function then where I drew my horizontal tangent there at these 2 points would be 0. Okay, now notice here that on the left side of this part where we had a 0, the original function was decreasing. That means it would be negative. Okay? To the right side, it is increasing slowly, then fast, and then slowly again. Okay, so it'd be like up and still increasing, which would be above the line, and then going down. So we're looking for something that's probably curving just like that. And then after it passes this or the horizontal tangent, it is decreasing. So it's negative, so it's going down. So the f prime x will look something like this. Right? It has two places where it has a horizontal tangent line, so there are two places where it's going to be 0. Right? And that is what your derivative function might look like when you sketch that derivative function on a graph, okay? So that's what it looks like. All right, let's continue our discussion. So let's think about the graphs of some functions and then think about what their derivatives might look like. Okay, so for this function right here, it looks like a quadratic. Notice on this side, it's decreasing on the left side. 0 has a horizontal tangent, so you know that there's going to be a 0 right there. It's going to be a 0. Here it is negative on the left side, and on the right side it's increasing, so it's going positive. So it's going to look something like that. All right, so this is what f prime of x would look like. Okay, for this other function, the next function, here we're increasing, so it's going to be positive. Here it is 0. Here it's again increasing, so it looks like it's going to be positive again. So just a rough sketch, your derivative function will look something like this. Okay, how about this third function? Here it is 0. Here's the horizontal tangent, so that's another 0. Here it's another 0. Okay, what is happening between these zeros? Here it is decreasing, so it's going to be negative. Here it is increasing, so that's going to be positive. Here it is decreasing again, so that's going to be negative. Right, it's going to be negative, and then it is increasing, so it is decreasing, then increasing. Right, it goes through 0, decreases, and then increases again. So your derivative function will look something like this. Okay, so that's what your f prime of x will look like. Oops, let's pull back down there again a little bit. Your 0 is right here. Let's pull this down a little bit, right? Because 0 was right here. So your 0 is here, 0 is here, and your 0 is here, right? And so it's increasing, 0 decreasing, and then back to 0. So it's going to look something like this, your f prime of x. And finally, for this one, your zeros, 0 derivatives there. Another one here. And another one here. So that's where your 0 derivatives are. And here it's decreasing on this side, which means it's going to be negative. And it's increasing, so it's going to be positive back through 0. And decreasing again, then increasing. So your derivative function will look something like this. Okay, so your f prime of x. All right, now let's continue. Talking about functions, it may be differentiable. If it's differentiable at a point, then it must be continuous. However, a function may be continuous at a point, but it may not be differentiable at that point. And two examples. One example that we can look at is function which has a sharp point. For example, f of x is equal to absolute value of x. It is continuous at x equals 0, but it's not differentiable right there. because of the sharp point here. As we looked at the example previously, it has two different slopes coming from the left and the right. The sharp point, you don't know exactly how to draw that tangent line, because its limit as h approaches 0 from the left and the right are different, then that means that it is not differentiable at that point. Same thing, but a similar, not exactly the same, but a similar idea is a graph where we have a vertical line as your tangent line, which is the case of f of x is equal to cube root of x. A vertical line as a tangent is undefined, so it's not differentiable right there. Let's take a look at higher order derivatives. We can take the derivative of a function, and we can also take the derivative of the first derivative that we took. When we take another derivative on the first derivative that we took, then that is called a second derivative, and then we can continue so on to take third and fourth derivatives up to nth derivatives. In terms of notation, your second derivative is f double prime of x, third derivative is f triple prime of x, but after third derivative, we tend to notate it as f raised to the 4 in parentheses of x. So that's how we write the fourth derivative. The nth derivative, f to the nth of x, right? And these are some other different ways of writing it, using dx squared y, du squared y over dx squared, and so on, just a way of notating it. Okay, now let's apply this to some other situations, such as velocity and acceleration. The derivative of a position function is a velocity function. Then the derivative of the velocity function is the acceleration function. So if you take the first derivative on the position function, you get velocity. If you take the second derivative on that function, or if you take the derivative of the velocity function, which is the first derivative of the position function, you get the acceleration function.